Hi, my name is Steve Harris, and I'm a resident of Rossmore. Thank you very much for joining me. If you want to get in touch with me, my email is on the bottom of the screen. Today I'm going to talk to you about what we understand about man-made or anthropogenic global climate change. My background is I have a PhD in physical chemistry from Harvard University, and I spent most of my career at the General Motors and Ford research labs in Michigan. In 2012, I was invited out by University of California, Berkeley to be a visiting professor in the chemistry department. And after that, and since then, I've been working at the Lawrence Berkeley National Lab. For the last 2 years, I've been a visiting scholar at Stanford. So I'm going to start by talking about what the greenhouse effect is, because that's the fundamental concept behind climate change. And then I'll talk about what we know and what we don't know about climate change and how accurate official climate predictions have been. And then I'll give you some of the arguments that are made against the idea of man-made global climate change, and I'll end with just a few sentences about what we might do about it. So first of all, I'm going to start with the greenhouse effect, but in order to understand that, you need to understand the relationship between heat and light. These are two forms of energy that can interconvert. And the easiest way to see that is if something gets really hot, it glows and gives off light. So I've got a picture here of a steel spike that's very hot. The hottest part is the brightest part, and it's yellow. And as you move toward the tip, you see it's getting dimmer, it's getting cooler, and it turns to only red hot. Until finally, when you get to the tip, it's cooled off enough so you don't really see much of any glow at all. Nevertheless, it's still very hot at the tip, and so it is glowing, but it's emitting light in the infrared, which our eyes aren't sensitive to, unless we're wearing infrared goggles, in which case all the infrared light looks green. Perhaps you've seen this in movies. No matter how cool things get, they're always glowing in the infrared. You and I and the ground are all emitting infrared light. In fact, on a typical night, the ground is emitting 400 watts of infrared light every square meter. That's like 400-watt light bulbs. And this is the way that the ground cools off at night, by emitting all this energy. Okay, so what is the greenhouse effect? First of all, the name greenhouse comes from buildings that are encased in glass. You put plants inside the buildings that like it to be warm, and so the inside of these buildings is going to stay warm even if it's very cold outside, as long as it's sunny. So a more familiar example of a greenhouse is a car that's parked in the sun. So sunlight comes down and strikes the windows. The windows are transparent, so the visible light from the sun goes right through and hits the upholstery, which warms up. So when the upholstery is warmer, it starts emitting more infrared light as it tries to cool itself off. But the infrared light is trapped in the car because the glass, while it's transparent to visible light, blocks infrared light. And so the inside of the car warms up. It's exactly the same thing with the Earth and the atmosphere. Light comes down from the sun, passes right through the air because it's transparent to visible light. And the light strikes the ground and warms the ground up, so the ground starts emitting more infrared light. The infrared leaves the ground, and whether or not that infrared can leave the Earth or not depends on gases that are in the atmosphere. Some gases, like carbon dioxide and water vapor, trap infrared light just like the windshield does. These gases are called greenhouse gases. So the global warming argument can be summarized in just 3 sentences. Compared to 100 years ago, the same amount of sunlight is coming in to warm the Earth. But because we have a lot more CO2 in the atmosphere, less heat in the form of infrared light can escape from the Earth, and therefore the Earth warms. Carbon dioxide has an important relationship to the ocean and to water in general, because if you have carbon dioxide in the air, some of it dissolves in the ocean. In fact, carbon dioxide dissolves in any kind of water, and this is how you get carbonated drinks. It's just water or some sweetener in which a lot of carbon dioxide has been dissolved. So it turns out that cold water dissolves a lot more carbon dioxide than warm water does. And the easiest way to see this is imagine you've got 2 bottles of Coke. One bottle you put in the refrigerator where it gets cold. The other bottle you leave out in the sun where it gets warm. Now when you go to the cold bottle and you pop the top, nothing much happens. And that's because there's a lot of carbon dioxide dissolved in the Coke, but it's cold, and so the carbon dioxide stays dissolved. On the other hand, if you open a warm bottle of Coke, you get a lot of fizz and bubbles. And that's because the carbon dioxide is unwilling to stay dissolved in warm Coke. And so the warm Coke actually expels the carbon dioxide, and what you see are all these bubbles. Now, since the last ice age, which ended about 10,000 years ago, the oceans have been gradually warming. And so all this time, they've been expelling carbon dioxide into the air. At the same time, because the oceans are warmer, more water evaporates. And so both of these greenhouse gases lead to a warmer planet. On the other hand, carbon dioxide is sort of like plant food. And because of the excess carbon dioxide, we get more forests that are growing, and forests then remove the carbon dioxide from the air. And so overall, we have just a slow increase in carbon dioxide over the last 10,000 years. And this is shown in the graph below. If you look at the left side, which corresponds to 10,000 years ago, you can see there's about 265 parts per million of carbon dioxide in the air. That means for every million molecules of air, there's 265 molecules of carbon dioxide. And if you look at the right side of the graph, which corresponds to about 100 years ago, you can see that there's about 280 parts per million of carbon dioxide in the air. So the amount of carbon dioxide has gone up only what seems like a very small amount, but carbon dioxide is a very powerful greenhouse gas. It absorbs infrared very effectively, and even that small amount of infrared light has helped reinforce the general warming of the Earth and given us a more pleasant environment. So I want to talk about what's called a positive feedback loop, which describes better how carbon dioxide and the oceans interact. So let's start 10,000 years ago. The Earth started to warm up at the end of the last ice age. And probably that's because there was some wobble in the orbit of the Earth around the sun, so that 10,000 years ago, we were getting a little more sunlight. So the entire Earth warms. And if you go down, you see a circle that says warmer oceans. Below that, when the oceans are warmer, they expel carbon dioxide and more water vapor evaporates. And you go down below that, and since you have more greenhouse gases in the air, that warms the planet. And now you loop up to the top. Since the planet is now warmer, the oceans are even warmer than they were, which means they expel even more CO2 and even more water evaporates. So you have even a greater greenhouse effect, warming the planet still more. And you go around and around in this cycle, and this is called a positive feedback loop. So the feedback loop has another branch, which is actually even more important. And this has to do with the fact that when the oceans get warmer, the Arctic ice starts to melt. The ice at the North Pole, it's called sea ice because it's just floating on the ocean there. That's as opposed to the ice covering Greenland or Antarctica, where under the ice there's land. So when the oceans get warmer, they directly start melting the Arctic ice. And so what happens is where there used to be ice, now there is ocean. And if you look at the photograph in the lower right, you can see regions where there's ice, which is white, and regions where there's ocean, which is dark. Now, white ice reflects light, so any light coming in from the sun that strikes the ice is immediately reflected back into space, and it doesn't do anything to warm the Earth. But when you have water exposed, the water is dark, and so that means it absorbs the light and gets warm. Well, warm water expels carbon dioxide and evaporates more water, which means more greenhouse effect, and so you enter the same a positive feedback loop. The amount of melting of the Arctic sea ice is pretty substantial. What these are 2 pictures showing satellite images of the Arctic sea ice superimposed on a map of the North Pole region. The lower graph shows the Arctic ice at the end of summer in 1986, and the upper picture shows the Arctic sea ice at the end of summer in 2012. About half of the Arctic sea ice is gone during the summer. And what that does is it exposes a lot more of the ocean, that dark ocean, to sunlight, all of which is now absorbing light and warming up instead of reflecting light. Positive feedback loops also run in reverse. So let's say someday the Earth will wobble again in its orbit and the Earth will get less sunlight, so it cools down. That means the oceans are going to be cooler and then going straight down. If they're cooler, they absorb carbon dioxide more. Water that's in the air will condense. That removes greenhouse gases from the atmosphere, which cools the planet, and then going all the way back up leads to cooler oceans. Or if you start at the bottom, where it says cools the planet, and go off toward the right, that's going to make more polar ice, which also leads to cooler oceans. And so in both of these branches, you go around and around, and the positive feedback loop reinforces whatever temperature direction it's going in. So what this is showing is that temperature and Arctic ice cover and carbon dioxide are basically locked together in a three-way positive feedback loop. And you can see the effect of this in the graph in the lower right. So this covers the last 400,000 years. And so on the left, it's 400,000 years ago. And in the red, you see a graph of the temperature during that time. And in blue, you see the carbon dioxide level. So wherever the temperature gets low, that's an ice age. What you can see here is that the temperature and the carbon dioxide levels are slavishly attached to each other. You can't get one without the other. And it doesn't really matter which one comes first. They have to go together. So what's our situation now? Well, we're at about 100 years ago, we were at about 280 parts per million of carbon dioxide in the air. And since then, people have been measuring the carbon dioxide level with considerable care. And so recently, last year, the carbon dioxide level was above 400 parts per million. So if you look at that graph I was just showing you, in the lower right, you may be able to see a red line that goes straight up. And that indicates that the carbon dioxide level is climbing very steeply. Now, as I showed you before, the Arctic ice is melting. The graph below shows carbon dioxide level is skyrocketing. And because these three things are locked together, one goes up, the others have to change, the temperature is also rising. And this shows the change in the global average temperature since 1880 on the left, and 2017, I think, is on the right. You can see a fairly steep temperature rise, especially since about World War II, which is in the middle, when industrialization really took off. Now, suppose we want to predict what's going to happen by the year 2100 in 80 years or so. So let's run through three possible scenarios. In the first scenario, tomorrow we just stop adding any carbon dioxide to the air. No more gasoline, no more coal at all. Okay, in this scenario, we're going to stay at about 400 parts per million of carbon dioxide for a few centuries. And that's because once carbon dioxide gets into the air, it doesn't really have anywhere good to go. Eventually, it'll dissolve back into the ocean, but that takes centuries. So what's going to happen then is the temperature will stay somewhere like what it is now, but over the next century or two, it'll drop back to what it was at the left side of the graph 100 years ago. Well, we're not going to stop using fossil fuels tomorrow, so we can consider a second scenario. Suppose we keep adding carbon dioxide to the atmosphere at about the same rate we're doing now. So I've drawn a yellow line, it's sort of a trend line, and that's about how much CO2 is coming into the air these days. So we can extrapolate that line to the year 2100, and what that shows is that we'll be at about 550 parts per million. And so what you see on the lower right is the prediction for the carbon dioxide in the year 2100 when our grandchildren are old. That's enough carbon dioxide so that the warming of the Earth is going to be quite a bit faster than it is now, and we'll end up 2 to 2.5 degrees Celsius or 3 to 4 degrees Fahrenheit warmer than we are now. Now, 3 or 4 degrees Fahrenheit doesn't sound like so much, but remember that that's sort of a global average, and some places may not warm at all, and some places may be warming 5 or 6 or 8 degrees. And that kind of temperature rise is enough to prevent some kinds of crops from growing very well. And if the farmers, wherever that happens, don't have the resources to change to a different crop, you can get serious crop failure. Well, the idea, this scenario that we're going to keep adding carbon dioxide to the air at the same rate we're doing now would require very aggressive cuts in the projected energy use, because India and Africa are just beginning to industrialize. If you look at this graph, you'll notice that around the year 1990 or 2000, the slope got steeper. More CO2 all of a sudden coming into the air. That's China coming online. And so if India and Africa do the same thing, then the slope of this line is going to get steeper. And so we can have another scenario, which is perhaps a little more realistic. And we say, what if our carbon dioxide production continues to grow at 1% a year, which is what it's been doing the last 50 years. So what you can see is these yellow lines are getting steeper. And if this is the case, then by the year 2100, the carbon dioxide level will be at about 1,000 parts per million, as shown in this graph to the right. 1% per year doesn't sound like much, but it means you double in 72 years. So, for example, that would mean that in the year 2100, we're adding more than twice as much carbon dioxide to the air every year as we're already doing. Now, in the scientific community, this is sort of referred to as a worst-case scenario, although in my mind, it's not so very unlikely. Basically, it just says we're going to keep doing what we've been doing. In this case, the average temperature rise will be around 3 to 5 degrees Celsius, 5 to 9 degrees Fahrenheit, and remembering that this means some areas are going to be hotter by 10 or 15 degrees Fahrenheit, it means some regions of the Earth are going to simply become uninhabitable, and for people who don't have air conditioning. And we might expect then that there'll be multiple millions of people who have to migrate. And as we've seen, large-scale migration is not good. Everything I've told you up until now describes what you could call a scientific consensus on global climate change. And so there's sometimes discussion in the press about what do you mean by a consensus. And so this guy, James Powell, in the year 2015, wrote an article. This is the title and abstract of the article. And what he did is he said, well, what are climate scientists actually saying? So he defines an active scientist to mean a person who is doing scientific research and publishing their research results in peer-reviewed scientific journals. That's our definition of a scientist. So then he looked at the years 2013 and 2014, and he asked, well, what are all of the scientific articles published anywhere in the world saying? And it turns out there are many thousands of these scientific articles, and they included more than 69,000 different authors who wrote articles in those 2 years. Of those 69,000 authors, only 4 of them rejected the idea that of anthropogenic, that is man-made, global warming. And so the consensus on anthropogenic global warming among publishing scientists is greater than 99.99%. It's essentially unanimous. Now, the fact that all scientists agree that anthropogenic global warming is real doesn't mean that they agree on much else. And in fact, there is vigorous debate in the scientific community over how fast the Earth is going to warm. And I'll give you an example of what this debate is like. A few months ago, there was an article published in a very prestigious scientific journal. And the article claimed that the Earth is actually warming a lot faster than all the other scientists had said. It only took 10 days for another climate scientist to debunk the claim. Science is an extremely competitive enterprise, and no one is going to allow someone else to make a wrong claim and get any glory from it. So, although there is debate about how strong climate change from human-caused climate change is going to be. There is no debate about whether it exists. And so if you become aware of a debate about whether anthropogenic climate change exists, then you can be certain that the people arguing that it doesn't include no scientists. So I've talked about a lot of the things that we know about climate change. Now I'd like to talk about some of the things we don't know, and there's quite a few of them. For example, we don't know when the ice sheets covering Greenland and Antarctica are going to melt. Probably centuries, but we can't tell for sure if it's going to be a few centuries or a lot of centuries. This is very important compared to melting of the ice cap in the North Pole, because that's floating on the water. And that doesn't add, when it melts, it doesn't add any water. Think of a glass of water that's filled with ice that's floating in it. If the water fills the glass to the top and the ice melts, the water still fills the glass to the top. There's no more water in there. On the other hand, if the Antarctic or Greenland ice sheets melt, that adds water to the ocean, and that's going to lead to rising sea levels. We can't make very good predictions on sort of less than continent scales of what the local temperatures are going to be. So we can't really tell you in 50 years Contra Costa County is going to be this much warmer. It's just too hard. And to get a sense of what that's like, here's a map of the world. These are temperature changes that have been observed between the years 1901 and 2012, 111 years. And the temperature tells you how much the climate has changed. Wherever the map is orange or red or purple, it means that the temperature is getting warmer. Purple is 2.5 degrees Celsius warmer. And wherever it's blue means that the temperature has been getting cooler over the last century. And for reasons that are mysterious to us, you can see Alabama and Texas have been getting cooler over the last century. We have no idea why that is. On the other hand, if we make predictions for large regions of the Earth, they're pretty good. So we can say that because of the ice sheet melting near the poles, there's going to be a lot more heat absorbed by the Arctic Ocean, which is going to warm the whole northern latitudes. And you can see that those have been especially warm. We also can't predict clouds locally and local rainfall. We can't predict whether there's going to be more hurricanes or not. What we can say is that in the future, the oceans are going to be warmer, so more water will evaporate. And in addition, the air will be warmer, so it can hold more water vapor. And so we expect that in the future, hurricanes, whenever they do show up, are going to be wetter. And we may already be seeing examples of that in recent hurricanes. And finally, we can't predict how much carbon dioxide there's going to be in the future, because that's going to be decided by political and economic factors that scientists aren't particularly privy to. The value of any scientific theory is based on only one criterion, and that's how well can it make predictions. Any scientific theory that makes predictions that turn out wrong is a wrong prediction, a wrong theory. And so every scientific theory needs to be tested against predictions. So as I mentioned, there's about 69,000 climate scientists in the world, and probably every one of them has their own prediction. So in order to bring some order out of chaos, in the 1980s, the climate science community formed an organization that they call the Intergovernmental Panel on Climate Change, IPCC. And the function of this organization, which included hundreds of scientists, was to evaluate all of the science that had been published up until then and try to come to some sort of consensus. So this group publishes results every 5 or 10 years, and their very first publication was in 1990. And so what this group did is they looked back to, let's say, 1970, as you see on the left part of the graph, and you see perhaps these thin lines that are red or green, and that represents different people, different groups that were measuring temperatures of the Earth. And so during the 70s and 80s, climate scientists were trying to come up with theories that could account for or explain this gradual temperature rise that they saw. By 1990, they had developed theories that seemed to agree with what had been observed. But the value of any theory is only in its ability to predict. So in 1990, they published a prediction for the next 30 years of what the temperature change would be. And there's 3 lines here that you can see. The solid black line is what they said is our consensus best estimate of the future of temperature. The thin lines above and below that represent sort of uncertainties. And so the projection was that the temperature, whatever it did over the next 30 years, should stay below the top line, above the bottom line, and the solid black line was the best estimate. And so what you can see is that as of 2017, the projection made 30 years ago is dead on. And furthermore, the variations from year to year that you see above and below that solid line have almost all stayed within the range predicted for the uncertainty. The IPCC also made predictions for the level of sea level rise, which is shown in this graph. The gray area shows the maximum and minimum expected value of sea level rise. That's the range. The blue numbers, where it says satellite observations, are the actual observed rise in the sea level. Again, the data show that the fall within the expected gray area, although it's really right at the top. And so what this says is that the climate predictions in 1990 were too conservative, and the theories need to be adjusted for what was actually observed. So in the popular press, you see lots of times you'll see arguments that are made against the idea of anthropogenic man-made climate change. And as I look at, there's dozens of these arguments, and as I look through them, I've categorized them into 3 groups. The first group is conspiracy theories. The second group includes scientifically invalid arguments. And the third group includes valid arguments that provide reason for skepticism. So let me start with the conspiracy theories. So the people who are involved in these claims believe that climate change is a hoax. It was conceived of by some nefarious group, maybe conceived of by the Chinese. And the climate data, all of the satellite pictures, all of the temperature measurements, it's all fake. And global warming is a worldwide conspiracy put together by climate scientists, all 70,000 of them in every single country in the world. So it's hard to make an argument against a conspiracy theory like this. In fact, since science is really an analysis of measurements, you can't really have a scientific discussion if people don't agree on what has actually been measured. And so I'm just going to pass on to the next category, which includes scientifically invalid arguments against anthropogenic climate change. So people in this group accept that the data is not fake, and so that they accept that, in fact, the world has recently been warming. But what they'll claim is that the warming is natural. It's part of a natural cycle. Maybe it's even about to turn colder. And crucially, that man-made greenhouse gases don't contribute in any significant way to climate change. So as soon as you make that statement about people in this group, you know that there are no scientists among the people in this group. So what they say is, we'll take the data, but the scientists just don't understand their data. And if you look at the data more closely, you'll see that the arguments that they make are not valid. So there's arguments in this class fall into a few different categories. One category is along the lines of scientists just don't understand their own data. And the most common argument that you see here uses the graph I showed you below, which graphs temperature and carbon dioxide in red and blue against each other for the last 400,000 years. And the argument is the following. Rising carbon dioxide levels can't possibly be causing global warming, because warming sometimes comes before the carbon dioxide levels go up. And so this kind of argument shows a lack of understanding of how interconnected positive feedback loops actually work. As I said before, it doesn't matter which one comes first. If the Earth warms first, we're going to get more CO2. If the CO2 comes first, we're going to get more warming, and we've gotten a lot more CO2 lately. Now, another class of arguments that are made in this category are what you could call cherry picking. So this shows the graph of the Earth's temperature from 1880 until 2012. So this is what the data looked like in that year. And in 2012, the Wall Street Journal ran an editorial that said, you know, the main argument against global warming is that the Earth isn't warming. Now, you might ask, how do you look at a graph like that and conclude that there's no warming? And so the way to do that is what's called cherry picking. So what they did is they picked out that particular year, which was 1998. And 1998 was the warmest year on record up until that time, and there was a big spike in temperature because there was a big El Nino that year. And then what they said is, well, using 1998 as our reference, we noticed that the Earth has stopped warming. There's the trend in yellow, and actually you might even say it's going down, and maybe the Earth is about to start cooling off. So one problem with a cherry pick like this is that why did you have to start with 1998? If you had started with 1999, you could come to the exact opposite conclusion, that the world is warming very quickly. You can't just pick one date. But the whole argument falls apart anyway, because in the last half a dozen years, the climate has resumed its steepening rise. It's sort of interesting to think about this 14-year period between 1998 and 2012. Every year during that period, scientists were producing temperatures which weren't really any higher than 1998. And this fact led the people in this category, opponents of the idea of global warming, to claim that the Earth had stopped warming. And for 14 years, the scientists kept feeding ammunition to the people who reject anthropogenic global warming. And perhaps if there was really a conspiracy to convince the world that there is global warming when there is none, then the scientists would have made up data that showed a sort of a more steady temperature rise. Okay, so there's a lot of other arguments that fall into these categories, but there's an overall strategy here which has two supports. First is the strategy tries to create a false impression that there is scientific debate. There isn't any. And the second part of the strategy is to produce arguments that sound sort of sensible, but aren't scientifically valid. And so it turns out that this strategy was originally developed for scientific analysis by an organization called the Heartland Institute back in the 1960s and 70s, and they developed it as part of their battles in the tobacco war. So the Heartland Institute was the largest non-industry funder of the claim that smoking was perfectly healthy. And it's not any coincidence that the same strategy is being used today, because today the Heartland Institute is the largest non-industry funder claiming that man-made climate change doesn't exist. Okay, now the third category of critiques are valid reasons for having skepticism of the climate change story. And I'll give you two important examples. The first one is that scientists, we can call them scientist politicians, like Paul Ehrlich or Barry Commoner, have a rich tradition of spectacularly wrong apocalyptic predictions. So Ehrlich back in the 60s and 70s was already claiming that by now half the world would be starving to death. And Barry Commoner claimed that by now we'd all either be choking on smog, or we'd all have to be walking around in gas masks. And these people just simply didn't take into account technological and regulatory changes. And unfortunately, there's still people in the climate community who are making these apocalyptic predictions based on the assumption that nothing is going to happen. The IPCC has tried to learn from the mistakes of these people. And so rather than saying, here is what's going to happen, they present scenarios and they say, if the CO2 does this, then this will happen. And if it doesn't do that, then something else will happen. people like Ehrlich and Barry Commoner have done a lot of damage, I think, to the credibility of the scientific enterprise, and it's incumbent on scientists to try and call them out. The second kind of valid criticism that you can level against climate change has to do with scientists who focus on uncertainties in the theories or in the models. And there's a couple of examples I'd like to give. The first is Professor Richard Lindzen, who was at MIT and was an eminent climate scientist, especially in the 60s and 70s. And what Lindzen pointed out is that people had done a very poor job of trying to predict and understand cloud formation in a warming world. So what Lindzen said is, look, the oceans are going to be warming, but when they warm, they're going to be evaporating more water, and that's going to lead to more clouds. Now, clouds are just like ice. They're white, and so sunlight that hits the clouds is going to be reflected right back into space. So this is going to be a negative feedback that hadn't been accounted for in the climate models. And so he argued maybe they're strong enough to counter all the warming that would otherwise occur. So in the last decades, climate scientists have taken this critique seriously and done a lot of studies on how cloud formation is impacted by warming oceans. And so the present-day climate models do the best that we can to predict how clouds formation is affected by warming oceans. Another critic of climate change is Judith Curry, who's a more contemporary climate scientist. And her focus is on the uncertainties themselves. Her idea is we have these uncertainties and we're claiming that we know what our uncertainties are. But that may not be very logical. How do we know how uncertain we are? What if there's something we don't know about? How do we know about things we don't know about? And so what she says is perhaps these uncertainties are much larger than we think, and perhaps these uncertainties will counter the global climate change story that we have. And this is a fair criticism. And yet, as I said, there's only one arbiter of whether a theory is any good, and that's, does it make good predictions? And so for all the flaws that these models may have, so far, for the last 30 years, they've been remarkably successful. And I think the skeptics who believe that climate predictions are very uncertain have to account for the success that the models have had so far. Okay, I'd like to conclude by talking about, briefly, what we can do about this situation. And there's a couple of different responses we can have. Maybe we can arrange to have less carbon dioxide in the air. And one way to do that is to regrow Amazon forests and have more forestation all over the world. And another approach would be to change our energy infrastructure so that we're using energy sources that don't require carbon dioxide formation. And those can include solar power, wind power, biofuels, or nuclear power. Another possibility is we simply adapt to whatever changes occur. They could include defenses against coastal flooding and development of crops that are resistant to heat waves and droughts. The problem with adaptation is whether or not the third world has the resources to accomplish these. Finally, there's some exotic technologies that may someday lead to a solving of the global warming problem, but we don't know yet whether these are going to occur. And so it's up to us now to decide what is our response going to be to this global warming problem. Thank you very much.